Okay, so let us continue to a very important portion of this unit, which is the calculation of resistances and capacitances when there are more than one transistor. So far we had only one transistor and it was easy. We have the definition and we have unit values. And now we are going to look at any general gate. So we have to look at the combination series or parallel. There's only two combinations luckily, and this is also going to be very similar to series and parallel combination of resistances. Okay, so let us look at the series case first, because the parallel case, as we will see, is actually very easy. Okay, series case, now I have two NMOS transistors and together we want to replace it with one transistor whose value is 1. So the question is, what should I put here and here? So let us start with one value. Okay, let us say I put 1 and I put 1. Now I can draw this diagram. Okay, and I have this transistor, I have this resistor corresponding to it. Its value is R, and similarly one more R. So which means that if you look at this whole network, it is equivalent to one single resistor whose value is 2R, because both are in series, and that's very simple combination. And this, if I go from the reverse direction, okay, I am going from a resistance to a transistor. What should I put for W by L here? Okay, such that I get 2R for the resistance. And how do we know that? We have to again look at that K1 diagram that we wrote. If I put resistance, if I put W by L equal to half, okay, this is not possible theoretically, of course, but just for the calculation, if I put W by L equal to half, that single NMOS transistor will have resistance R, okay, divided by half, and this is equal to 2R. And this is fine, but this and this, they are not matching, right? I have half here, but I want to get one single NMOS transistor whose W by L is 1, which means that all the things that we did starting with here are not correct. So let us remove those parts alone, and let us remove this, and let us see what we can do. So we want, now you know what we want. We want to get, okay, let us go in the reverse direction. We know that this is one, okay, and one corresponds to just R. Now let us go in the reverse direction, meaning I want to go from this diagram to this diagram. I want this to be split into two resistors such that they add up to R. So obviously I have to put half R, not anything else. Okay, if I have R by 2 and R by 2, it will add up to R, and then all this matches. So the only thing now I have to do is finish off the diagram and go from the resistance to the transistor, which means that I have R by 2 and I have to put something here that will give me R by 2, and that I know is very very simple, 2 and 2, because whatever is here, that comes in the denominator. So resistance corresponding to this is R divided by 2, which is R by 2, here also R by 2. So this is my overall equivalent system for two transistors. 2 2, if I put, that is the same as putting one transistor with W by L equal to 1. So these two series transistor and this single transistor, they are equivalent to each other, because if you look at the resistances, they are the same. Okay, and this is the series case. Here is the parallel case. Now parallel case, the little bit of extra problem is that we have two branches, okay, and they can conduct in many ways, meaning that in the network one branch can be conducting either one, that is left hand side or right hand side, or both branches can be conducting. And now you will ask me, how can we then find out what is the equivalent resistance, because there are many cases. So whenever we have the parallel case, okay, all the time, NMOS, PMOS, whenever we have parallel, our life becomes very simple. You just have to, whatever you have for the equivalent single transistor, put that here and here, and it is done. Okay, because now in the worst case, which means that, for example, if this branch is not conducting, okay, so this whole thing is open circuit, I have only one branch conducting, they are equivalent to each other. Opposite also could have happened, this could not be conducting, this might conduct, then also they will be equal. And if both are conducting, then that's going to be slightly different, but we won't worry about all that. When there are parallel branches, we will just use the single NMOS transistor or PMOS transistor, and we will put it as 1. Okay, so this is true for many more also. I could have a third branch in parallel. Okay, I don't have to worry about that. It will still be, how much should I put here? 3 and 1. So now there are multiple branches. 2 can be conducting, 1 can be conducting, 3 can be conducting. A lot of confusion. Let us not worry about all that. Simplifying assumption, it is still going to be 1 1 1. Okay, so this is the way in which we can convert series parallel transistors into single transistors. Now why is all this important? We have to go back to our question. What is the question? Two input NAND gate. Okay, size it so that the delays are comparable to a unit inverter. So we will go back to our whiteboard and we will just draw the gates first. Two input NAND and a single inverter, and they should be equivalent to each other. Okay. While I'm drawing, you can just think about how we can go about achieving that. And like I said, from now onwards, along with the circuit, we need the W by L. And unit inverter definition is fixed 2 and 1. Now let me draw a 2 input NAND gate. Okay, finally, so now we have the both the gates. One side we have the sizes, the other side we have the gate. Okay, that's fixed. And what is the requirement is the PMOS and the NMOS should be given sizes. Okay, not just any sizes, such that the left hand side and right hand side are equivalent to each other. That is, the overall resistance of the network should be the same. And this we have already done for the NMOS part. So directly we will write, we did the example where one single NMOS of size 1, if I have series transistors, it becomes 2 and 2. So these two together is the same as one single NMOS transistor of size 1. Okay, now PMOS transistor, like we discussed, parallel is very simple. Okay, if I want multiple parallel transistors to be equivalent to a single transistor, we just put the same number directly, 2 2 2 2. That's all we need to do. And this two input NAND gate is equivalent to a unit inverter? So the first part of the question we have answered. Draw a 2-input NAND gate and we have given the sizes. The delays are comparable to a unit inverter. Now let us repeat for a 2-input NOR gate. Okay, so we'll remove this part and we need a NOR gate this time. Okay, so 2-input NOR gate, and now we want it to become equivalent to the same unit inverter again. Now we have the NMOS transistors are in parallel, and these two parallel transistors should be equivalent to this single one. So as we talked, don't have to worry at all. Same in W by L put for both the transistors. Now we have the pull-up network. Two PMOS transistors, one single PMOS transistor. So what is the value of this resistance? Its value is 2R by 2 or R. Now I have two transistors and I have to give for each of them how much? R by 2. Okay, I have to give R by 2 to this transistor, I have to give R by 2 to this transistor, so that when I add them, because they are in series, I will get R. So now how much should I put for the PMOS transistor so that it becomes R by 2? So for that, PMOS transistor resistance is equal to 2R divided by K. Okay, this is the resistance of the PMOS transistor, and this should be equal to R by 2. That is my requirement. Now it becomes very simple. Cancel off the R. Okay, so cross multiply and I will get K should be equal to 4, and the same thing here also. So this is the equivalent 2-input NOR gate for a unit inverter, not just any inverter, unit inverter. So we have 2-input NAND, 2-input NOR, and we have drawn the equivalent gates: 2-input NAND gate, 2-input NOR gates. Next question, definitely go from 2-input to 3-input. So what is this question asking? First part is 3-input NAND gate, okay, equivalent inverter. So let us do only this part first. 3-input NAND gate comparable to equivalent inverter. Then we will see rest of the question. So I will leave the equivalent inverter because we want to compare it with that. This time I want a 3-input NAND gate. Okay, so first I will draw the 3-input NAND gate and then we put the sizes. Okay, so we have got the circuit, 3-input NAND gate, and let me give you a couple of minutes. Okay, try to finish this diagram. We want the sizes, and we have these three. It should be equivalent to this single transistor. Similarly, these three should be equivalent to this single transistor. Top part I'll do if you want, very simple. So we can just put the same numbers everywhere, 2, 2 and 2, nothing to do at all. Bottom part you have to do a little bit more work. Okay, 3 transistors are there, and each of them will have resistance, resistance and resistance, and together they have to equal R, which means that each of them has to equal R by 3. So R by 3, R by 3, R by 3, together if you add all of them you will get R. So this and this, they should be the equivalent to each other. R by 3, I have NMOS transistor, I should put the W by L, okay, and I should put the W by L such that its resistance becomes R by 3. So what should I put for the W by L here? And this is where that W by L R relation is important. If you want to increase the, sorry, if you want to reduce the resistance, you have to increase the W by L. You keep increasing the W by L, resistance keep reducing, directly proportional. So which means that I just have to go with 3. Okay, same here, here and here. So R by 3, R by 3, R by 3, same as this, which is equivalent to this. So this is my gate, 3 input NAND gate equivalent to unit inverter. So this is the perfect equivalence in terms of NMOS and PMOS. Okay, and this is the first part of our question. 3 input NAND gate sized with delays comparable to unit inverter. Next part, we have done this before. Mark all the capacitances. Go back to this diagram. Okay, now we have multiple capacitances. Like I said before, important thing to remember, 3 capacitances per transistor. Okay, and if they are connected between the same terminals, then there is no need to mark them like we were doing before. So we will start with the top part, PMOS network. Now this terminal, this terminal, this terminal, all 3 capacitances we will not mark, okay, because this terminal is already connected to VDD, and since the other terminal of the capacitance is also connected to VDD, there will be no need to mark that capacitance. But other side we have to mark the capacitance. So one capacitance here, one capacitance here, okay, and one more capacitance here. And I don't need this inverter anymore, so for now we will just remove this. Hopefully I don't need to use it again. Okay, and this, all the PMOS transistor has size 2, which means this and this, all the 3 transistors will have a capacitance 2C associated with that terminal. Okay, and next thing is, we don't have to worry too much about the gate capacitance because it is not connected to the output node. I will not draw this every time. Okay, so these capacitances are not part of the output node, so we don't need to draw the capacitance. There is a capacitance, if you want I can just show it here. Okay, its value is also 2C, but since it is not connected to the output node, it is not going to contribute to the delay, so we don't have to draw it. So this is the pull-up network, 3 capacitances here, all the values are 0. Okay, so we don't have to draw that. Now let us come to the pull down network. So we'll start with this side. Okay, and its size is 3, which means the value of this capacitance is 3C. Okay, now we have to be little careful. 2 transistors are in series. Okay, now let us remember what the layout will be like if 2 transistors are in series. Okay, and we have the layout. Now this part which I am shading, okay, is the middle part here. Now if you say I'm going to put 3C for this transistor and 3C for this transistor, that will be wrong, because whenever you have two transistors in series, the same terminal is shared. They don't have two separate diffusion terminals. One for, I will not divide this in the middle and say this is for this side, this is for this side. No. Okay, we will just share the same transistor. So this is the width. In this case it is 3. Okay, that is here W by L equal to 3. So the same terminal is shared by both transistors. So for both transistors together, okay, important thing to remember, there is going to be only one capacitance. And what is the value of that capacitance? It is not 3 plus 3 6. It is not double because they are shared, which means that it is going to be a single capacitance of just 3C. And the same thing here also, one single capacitance, okay, shared between the two transistors whose value is again 3C. So 3C here, 3C here, 3C here. And I didn't have to draw it because it's not connected to the output node, but because it's an important concept, I just wanted to show it to you. So these are all the capacitances associated with the transistor. Again, I'm not going to draw the gate capacitance. Okay. Mark all the capacitances. Show the equivalent RC circuit for falling output. First, let us do the falling output. So we'll go back to this diagram. Okay. And we'll erase this part because we just want the falling. Okay, so we'll say falling. Falling means the output is going to 0. It has to happen through the pull down network, which means that there cannot be any combinations, meaning we have three transistors. If the output is falling, the only possible case is all three transistors are conducting. Okay, I cannot have two transistors conducting and the output falling because it will be open circuit, it will not reach the ground. So for the falling case, okay, first transistor, second transistor, third transistor, all three of them are conducting. Number one. Number two, if all three NMOS transistors are conducting, all three PMOS transistors are not conducting, which means the whole top part, okay, is completely disconnected. There are no transistors in the top. But don't forget the capacitances. Okay, I have three transistors. To find out the equivalent network, I have to mark what is the value of this load capacitance. And load capacitance, like we did before, is just the sum of all the capacitance that are connected to the output node. So I have to look at not just the pull down network because I'm doing falling. Even these transistors, these capacitances are connected to the output node, so they also have to be considered as part of the load. Okay, so how much is the value of each of these? 2C, this also 2C, this also 2C. So the pull-up network offers a total capacitance of 6C. Okay, 2 plus 2 plus 2. And the pull-down network, okay, these capacitances, even though we have marked, they are not part of the output node. I only have to calculate the first capacitance, which is directly connected to the output node. So that is going to be plus, how much is the value? 3C. So the total output capacitance or the total load capacitance in this case is 9C. Okay, and what is the question asking for? Show the equivalent RC circuit. Okay, falling output. And if you want, you can also say delay equal to how much according to the RC delay model. Okay, capacitance is 9C. What is the total resistance? R by 3, R by 3, R by 3. So it is going to be nothing but 9 RC. This is the delay according to the RC delay model. That is the equivalent circuit. Output capacitance is 6C plus 3C is 9C. This is for the falling transition. Now go back to the question. Okay, best case and worst case output. So this is something that we didn't anticipate. Okay, so let us go to the rising transition. Let us start with the best case. Okay, rising transition. So what is the meaning of best case and worst case? It's very simple. Okay, there are three parallel branches, and of these three parallel branches, the worst case is when only one branch is conducting. Okay, and in addition to that, we have in the pull down network three capacitances. 3C is connected to the output node. Okay, obviously the first capacitance, this one, it has to be charged. If the output is rising, this is connected to the output node, so definitely this has to be charged. But the worst case means not only the output capacitance, but some more capacitance. For example, this one also, which means that the first transistor is conducting. Okay, this transistor is also conducting, which means that this also has to be charged, plus this also has to be charged. So this is the worst case when I have three transistors. Okay, and CMOS circuits are such that only one of the two, pull up network, pull down network, both cannot be conducting. That's a given fact. But if I have only one PMOS transistor conducting plus these two NMOS conducting, it means that I have to charge this capacitor, that is a given, but in addition I have to charge this capacitor and this capacitor. Okay, and all of them have to be charged through only one single PMOS transistor. So that is the worst case. Sorry, I'm explaining worst case to begin with. This is not the best case. So let us just change this. Okay, so what we're doing so far is the worst case. Only one single transistor conducting in the pull-up network plus more than one or the worst number of intermediate nodes also being charged. That is going to give me the worst case delay. So for that, it's going to be, this is the output node and one transistor conducting here, one more transistor conducting here, but the last transistor is a open circuit, and this is the worst case delay. So in addition to the output node capacitance, this capacitance and this capacitance, that is here and here, also have to be charged, and all of them have to be charged through the single PMOS transistor. So this is the worst case delay. Similarly, we can also do the best case delay. Okay, this is the exact opposite. We have all three transistors conducting and all of them not conducting. So this is simpler to draw, or simpler to analyze rather. Conducting, conducting, okay, and this is also conducting, and only the output capacitance is charged. All the others are open circuit. This is the open circuit, open circuit, and the next one is also open circuit connected to ground. Okay, so 1 2 3, yeah. So this is the best case. And these are the configurations that they've asked in the question: best case and worst case for the output, following only one case when all are conducting. Okay, now whatever we have been calculating using the previous few diagrams, few cases, this is the RC delay model. It's one way to calculate the delay. Okay, and it's the simplest by far. and it's about say 70% accurate to the actual number. But one thing that you might have thought about, okay, whenever we are doing the delay calculation, we are putting 9c, and best case, worst case, if you look at the RC delay model, there is no best case, worst case, there's only one case. But as we just saw in this example, it's a best case and there is a worst case, and the delays are going to be different. So how can we account for those also? Main problem with the RC delay model is that the intermediate capacitances, that is, this is the output node, but these are also capacitances that are going to create some problems. So those capacitances, they are not being used as part of the calculation. That is the main problem with the RC delay model. Why the accuracy is not very good? This is completely ignored. If you look at the delay equation, okay, you don't care about this capacitance. We don't care about this capacitance also. But just as we saw in this example, there is going to be a best case and the worst case. The delays are going to be different. So the RC delay model is not going to give us all those answers. For that, we have to go to the next delay model, which is also called as the Elmore delay model. And Elmore delay model is a very popular delay model even in computer tools, because it gives a very good answer, okay, maybe 90% accurate, but it takes only a very small amount of time compared to a simulation. So we have some clock tree networks. These are the most popular cases where the Elmore delay model is used. I have a clock tree network. Clock tree network means somewhere the clock is there, okay, maybe it's being supplied by some particular clock driver, and they might be say very easily, this is not a random number, but very easily they might be even 1,000 plus terminals that are being supplied by the same clock driver. And at each of these points, okay, we might want to require the delay. If the circuit is a synchronous circuit, then the delay of the clock at each of those points should be the same. That is the definition of synchronous. Okay, so Elmore delay model is just another way in which we are going to calculate the delay. And the most important difference is, in the Elmore delay model, somehow we are going to include the intermediate nodes. Okay, we have many nodes in a circuit. If you look at, for example, in this circuit, if you look at the pull down network, it has one, two, three nodes. Okay, one of them is the output node. RC delay model takes the output node only. It completely ignores this node. Okay, oh sorry, and it completely ignores the intermediate nodes. So we have one intermediate node here, one intermediate node here, and each of these, as we have shown earlier, has some capacitance that is associated with it. Here there is 3C, right, and here also there is 3C. So we have to use these nodes also into the calculation. That is the main difference between Elmore delay model and RC delay model. Now in Elmore delay model, these nodes are also going to come into the picture. Okay, but only question is, how much do they contribute? We have delay. Delay always is in terms of RC delay only. Okay, that is not going to be different. Every capacitance is going to contribute some delay. What is the value of the delay? It is given by R and C product. So if you look at this circuit, for example, output capacitance is 9C. What is the contribution of that capacitance? That is equal to 9 RC. That is okay. Same RC delay model also, that is this. Now Elmore delay model, this term is going to be there, okay, but in addition, now we have two more. We have this capacitance, we have this capacitance. How much are they contributing? That is the question. And for that, we have to look at the definition of the model. Okay, it looks a little complicated, but it's actually very simple. Each capacitance is going to contribute some non-zero value. That is what we have to remember. Okay, and the total delay is just the sum of all those terms. So, for example, if you look at the bottommost equation, I is nothing but all the nodes in the circuit. So we have 1, 2, 3. So if we did the summation of Elmore delay model for this particular equation for this circuit, I will have three terms: one term, two term, three term. First term, output node 9RC, that will be the same. Okay. Now second term, the capacitance value is 3C. Okay, that is fixed. This is also 3C, that is fixed. So the second term, what is the contribution? Ci is 3C. Okay, because I is the second node, and Rij, now this is where there is a concept of shared resistance. Okay, Rij is the total resistance that is on both parts from the root to the node I and the root to node j. So what is the root? Root is nothing but where is the signal. Okay, so the signal is being supplied at some particular point in the circuit. And if you look at this diagram, for example, this is the root node, because if you look at this network, this is the pull down network, which means that we want the output to be pulled down. So we want the output to go from high to low. Where is the low? Source. This is the source. So this is the root node for the pull down network, and this is the output node. So if you go back to the definition, Rij is the total resistance that is on both parts. Okay, root to node I and root to node j. So what is I? I is what is changing. That is, every time we come from one node to another node, I will keep changing. Okay, so R of Ij, that is between two nodes I and j, what is the shared resistance? So for that, again we have to look at two paths. Rij is nothing but the shared resistance. What are these two paths? First is from root node to I. I is in this case, so for example, if I'm at this node, this is the root node, this is the node I. What is the shared resistance? It is, this is the path. Okay, from a root node to node I, and the other one is the delay component at node j is given by root to node j. Root is the same. Okay, root cannot change. This is the path from root to node j. I have two paths. This is the root node. We have to identify, okay, based on the signal transition, whether VDD to ground or ground to VDD. Then we have to calculate what is the shared resistance according to the Elmore delay model. What is the shared resistance? They have defined it as a term which is common to both the paths. So this is one path. Okay, this is from this node to this node. It has three resistance: one, two, three. The other path is from here to here. How many resistances does this path have? It has these two. So what is the shared resistance? Okay, where is that? Okay, I think it's the previous slide. Okay, let's not worry too much, but common to both the paths. That is what is called as the shared resistance. So for that, we just have to see here these two resistances are common to this path and this path. So what is the contribution of this capacitance? That is the sum of these two, or R by 3 plus R by 3. That is 3C into R by 3 plus R by 3, or 2R by 3. So that will be 3C, okay, into 2 by 3R. So this is the contribution of this particular capacitance. And now we can go to the next node I. So look at the equation. This is along all the nodes I in the pull down network, for example, and this time the shared path is, this is the path from the root to node I, because now I has changed to this node. So this is one path, this is the other path, still the same because J did not change, root did not change, but now the shared resistance has reduced. It is only R by 3. So that contribution is going to be 3C into R by 3, and therefore the total delay is given by 9 RC, which is the delay due to RC delay model, same delay. In this case it is the delay due to this node. Okay, now the rest of it is 9 RC plus this is 2 RC and this is RC, so the total delay is 12 RC. This is the worst case delay as predicted by the Elmore delay model. RC delay model, worst case, best case, all cases are the same, equal to 9 RC. But we know from our analysis of circuits that that is not true. Internal nodes also will contribute to the delay. How much they contribute, that is what the Elmore delay model lets us calculate by the concept of this shared resistance. There are two paths, one from node to the output node, root node to the output node. Another path also from the root node to the node I where the capacitance is connected. How much ever is the common between the two, only that much resistance you put. So in one case we put R by 3, one case we put 2R by 3, another case full R, because in that case both the paths were the same. So both of them had the same amount of resistance, R by 3, R by 3, R by 3, that is this case. So the total resistance, the total delay is a sum of all those three, which is what we see here as the summation term. And in this particular case, the worst case delay is given by 12 RC. Okay. So we will stop here and